the effect that high intensity sound pressure levels may have on workers, because in our opinion it's irreasonable that people going to work may be damaged by the noise produced by the work itself, because we want to provide a safe environment in order to avoid any kind of health disease that to these people that basically are just making their duty. So let's start with the presentation. Great, one more. Just I'll give you a little summary. I'd like to schedule this presentation today. The first point, noise pollution affecting human health. Just a couple of keynotes, which may be the most common disease connected to the high sound pressure level, impulsive noise, and from a medical point of view. So a little overview of the disease that may happen to people subjected to this kind of noise. Then, I know it's a little boring and it's not a faculty of medicine, but it's important to know a little about the anatomy of the ear, so more or less how the sound transmission works in our auditory system. And then comes the psychoacoustics, which is basically the study of acoustics connected to human behavior. It's like a borderline subject, borderline topic, because try to match the descriptors, physical descriptor we talked about yesterday, with the behavior, with the fact that this sound pressure level, with the fact that these indicators may have on the people. And of course, because we are talking about interaction between people, person, and sound, we need to define a new kind of descriptors. This presentation is about basically a rant, so a kind of we'd like to point out some deficit.
No, I don't know.
Prova. Okay, it was a pleasure. See you next time.
One moment, Alessandro.
Solamente se apaga el enfoque. Ah, ya, chévere, chévere.
Creo que te está acercando.
We're talking about legislative scenario because we want to point out the weakness of the European directive, and we try to point out if the European directive is effective or not about the protection of workers. Okay, noise up to a few years ago wasn't considered a pollutant, so if our environment was noisy or not, no one cares about. But it's clear that in the last year, noise has become a prominent feature of the environment. That means that noise, it became a big problem. People start complaining about this problem. And in particular, noise, as we see yesterday, is due to transportation problem, so road traffic. If you want, you can get my slides, so there's no need to just take a picture of the screen. You can go and you can give my slide to everyone. Yes, for it then. Industrial activities, and of course working place. Exposure to noise may create for sure harmful effects depending on the characteristics of the acoustic phenomenon. So sound pressure level, of course, if a person is exposed to a sound pressure level of, let's say, 70 decibel, it's not so risky as a person that is exposed to a level of 120 decibel. You can feel by yourself going to a club, to a disco, try to stay in a disco, try to stay in a park. The difference is quite clear. Then there is the frequency, because human hearing detect sound in different way depending on the frequency of the sound. As you know, the sound is composed by several frequencies, so from 60 to 20 kilohertz, which is the audible range of our auditory system. It's quite difficult to find a pure tone, that means a sound made by just one frequency. So every frequency affects our hearing system in a different way. Then comes the impulsive noise, because a really problematic since our ear cannot protect the system from this kind of situation. And of course, this harmful effect depends on the exposure time. It's better to stay in a noisy place less time than stay for like 8 hours, 16 hours all day long. And because we are talking about people, the effect depends on the subjective sensitivity of the person. To sum up everything, we can say that the noise may produce two different kinds of effects on the human health. Hearing loss, which is clear because if you stay in a loud place for too much time, you may simply lose your hearing function, or general problems. Okay. It's clear that when we stay exposed to a loud phenomenon, a loud sound, the principal effect that we can feel is the hearing loss. That could be temporary if the sound is not so much loud, or of course could be permanent. And this is just the first kind of effect that we can think about when we talk about noise control. But as you can see, there are several health problems such as hypertension, problem to the heart, so ischemic heart disease, vasoconstriction and other cardiovascular adverse effects, annoyance, sleep disturbance, which are connected to the social behavior. Because trust me, if you cannot sleep well at night because of traffic, because of noise, the very next day will be really tough to get up, to make your job, and everything else. So noise can produce sleep problem, even affecting change in the immune system. And the last study made by the Health Organization has proved that noise may affect birth defects. And many times, in the past especially, the risks coming from noise pollution were underrated. So there weren't too much protection for people, especially workers, when they are exposed to loud sound pressure levels. Okay, now I know it will be a little boring, but you have to know all this stuff, at least in a general way. So this is the schematic of the human ear. You can see basically it's divided in three main parts: the outer ear, so the external part, the middle ear, this one, and the inner ear. The outer part is made by the pinna, which is basically a kind of parabola that collects sound waves. The auditory canal, which drives the sound from the pinna to the eardrum, or even called tympanic membrane. The tympanic membrane is the division between the outer ear and the middle ear, and it's composed by these three systems, which are bones. These three are the smallest bones presented in our body. They are like microscopic. And their suction tube is the connection between the tympanic membrane and the throat. And you can experiment this suction tube when you're on a plane and you change pressure. There is a fast change in external pressure. You can feel your ear eyes that they were tapped by something. So this channel allows a compensation of pressure between this part of our body and this part of our body. To conclude, there is the inner ear, which is made by, this is just an introduction, because then we are going to walk through all these three parts in detail. It's made by semicircular channel, the cochlea, which is basically the system that allows us to feel sound and to detect sound. And the neuron, which is the connection between the cochlea, so the sound will coming from outside, and our brain. Okay, this is a little picture of the outer ear. As you can see, it's made by the pinna, which is a cartilaginous part. You can just feel yourself. The meaning of the use of this anatomic part is simply to connect sounds coming from different positions, from different paths, and drive this sound through the channel, through the eardrum. The acoustic meatus is characterized by a resonant frequency. I don't know which are your knowledge about mechanics and about resonance frequency. But everybody, because of the mass, because of the stiffness, is characterized by a resonance frequency, which is basically the frequency at which the system starts to amplify its vibration. And because of the resonance effect of the ear channel, the sound can be amplified in the path from the pinna to the eardrum, which again is the division between the outer part of the ear and the middle one. The anatomic part that divides these two areas is the membranic, is the tympanum or membranic tympan. It's simply a cone shape, so it's a cone membrane fixed to this part, which are bones, and it's the part of this temporal bone is one of the 6 bones that compose our brain cave. And it comes to middle area. It's really important, this part. As I told you, these are 3 bones. One, the ulnar, the incus, and the stapes are the smallest bones present in our body. And their function is to transmit the vibration collected by the tympanic membrane. As you can see, here is the connection with the membrane, with the bony part of our body, with the temporal bone. Transmit this vibration through the inner ear. Okay, the name is quite obvious because hammer is like an hammer that impacts an incus and transmit vibration to this little bone called stapes, because it's exactly like the stapes you use for riding a horse. So there is not many fantasy in the name of these anatomic components. But it's important to note that the presence of these 2 muscles, the tympanic tensor and the stapedius muscle. We are going to talk about these 2 muscles in detail later on, but just to give you an overall idea, the tensor tympani is a muscle that can change the tension of this membrane. So if a sound is too loud, the tensor tympani will release the membrane, so the sound will be somehow reduced in amplitude. While if the sound is is not so loud, it's very as a small amplitude, the tensor tympani simply make this membrane stiffer, so the vibration could be transmitted in an easier way. Just think about drum when you try to pull the material of which drum is made of. While the stapedius muscle, this one, let's see, I can put this here, can increase or reduce the oscillation of these 3 bones, and in this way the transmission of the sound can be increased or decreased depending on the intensity of the sound itself. And then comes the inner ear. So just to sum up, we got the sound coming from the pinna, which is more or less here, coming through the ear channel on the membranic tympanic membrane. Well, you know, sound is like basically a vibration. It's the oscillation of a body around its middle position. So when a sound impacts another body, makes this body moving. This movement is amplified by these 3 bones, the malleus, the incus, and the stapes. Now, this part, the blue part, is the inner ear. It's made by basically 3 main parts: the vestibule, which is here, the 3 semicircular channels, which are responsible for the balance of a people. You know, when you sometimes you feel like vertigo, because in these 3 channels, which are around each other, there is like a fluid, and you can detect, and this fluid can detect your motion, so it can prevent the feeling of vertigo. And the last part, the most important one, is the cochlea, here, this vortex, which is the real organ responsible for the hearing phenomenon. So, keep back, just making a step back. This pressure is collected by the tympanic membrane. It's transmitted by this system, these 3 bones, and here is a fluid. So if I apply a pressure to a fluid, what happens? Just physics 1. So, if I apply a pressure to a fluid, what happens to a fluid?
Se aplica una fuerza a un fluido que
Okay,
pasa
basically
por
can
el
transmit
fluido.
the sound, the vibration through this pressure change to the cochlea.
Se contrae.
And now we start with a really funny part of anatomy. This picture from Grey's Anatomy, which is not the TV series, it's just a book. As you can see, the cochlea, which is the real organ for detecting sound, is a coiled tub, so it's like a spiral, divided in two portions: the scala vestibuli, which is the higher part, and where is the tympanic or tympani, scala tympanic, here, which is the lower part. These two portions are divided by a membranous partition, which is this one. So we have upper part, the scala vestibuli, lower part, we got the scala tympani. In the middle, we got this, which is called cochlear duct. These two portions, I mean the scala vestibuli and the scala tympani, are divided through all their length. So they are always divided by this system, except for their top, where there is a little hole called helicotrema that basically allows fluid to move within the thorax. So if I've got fluid in the upper part, in the scala vestibuli, this fluid moves to all the cochlea. So start here, goes here, then will be here, then will be here, then will be here, and then here is a little hole. I hope you can imagine this. And the fluid can move to the lower part, to the scala tympanic. So will be here, will be here, will be here, will be here, will be here. Okay? And through this question? Over there? Last line? No. Okay. So, we're talking about this mechanism. The fluid moving through this section allows the detection of the sound, because the scala vestibuli is filled with this fluid called perilympha, while the cochlear duct is filled with this fluid called endolympha. You can see the main component of the cochlear duct is, of course, this organ of Colci, named after Luigi Colci, I guess, an Italian doctor, which in the 18th century loves to open crops of dead people and dead animal to check how our body was done. And it is for this section, which is the real effective responsible for detecting the sound pressure level coming from outside. In detail, this is a section of the organ of the Corti. I know, every time I look at this picture, reminds me about Jabba the Hutt of Star Wars. It's really ugly, but it's really effective at the same time. What happened? Here, there is I died, I hope. There is this portion, the scala vestibuli, okay, which is filled with this fluid. This fluid is pressurized because it can detect the vibration coming from outside. So if a pressure change happens here, this pressure will be transmitted to this part, which is filled with another fluid. And I told you that vibration, so pressure, can be transmitted to the fluid. So changing pressure in this area means that this part, called pectoral membrane, start moving, okay? If I apply a force here, okay, this pressure will affect this part, the pectoral membrane, which is going to impact these little guys called air cell. They are cells made of air, and they can transmit the stimuli, so the electronic impulse, from this membrane to this other area, which is called the galileo del corti. It's an Italian word that basically cannot be translated anymore. As you know, this cell can transmit electrical input or electrical impulse. So when this little cell will hit this part, we close this circuit. It's like an electrical circuit, and we can transmit this difference of potential from this point to this point to the basal membrane, which is somehow through this cell of daters connected to the this one, which is the acoustic nerve. That it's basically a nerve that connects our ear to our brain, so we can this system allows the sound, which became an electrical signal, to go and be detected by the brain. I guess that would be everything about this picture. Let me check. Yeah, because this basilar membrane runs through all the cochlear duct, and it allows the transmission of vibration from the scala tympani to the organ of Corti. So just to sum up one more time, the pinna, which is the outer ear, collects the sound waves to the auditory channel. The sound basically produces a vibration of the tympanic membrane, and there are no change in frequency and amplitude, so this system doesn't change the frequency of the sound and the amplitude, and it's really important, because if the tympani could change the frequency of the sound, we can detect simply a different kind of excitation. So tympani doesn't change the input signal. Then comes the ossicle, or the three bones, which transmit the signal, the pressure, to the oval window. And again, there are no change in frequency in the amplitude. There are no change in frequency while the amplitude is reduced. This happened for these four reasons. If you remember the picture of the ossicle, do you remember more or less? Or should I go back to the slide? Remember, okay. They are like a lever with a factor of 3, because the ossicle are more closer to the oval window, so to the inner ear, than to the tympanic membrane. It's like try to lift something using a lever. How can I show this? You know Archimedes? Basically, if I put something here, and of course I can lift this. No? This system is like a lever. You know what lever is?
Yes. Escalera.
I don't know which is the stage for lever, but I guess it's just basically a piece of metal with a powerful inside, and you can lift stuff. Yeah, this system is like a lever. Okay? Now, if you go back to your notes on mechanics, you can check that this kind of lever, for how it's built, it has an amplification factor of 3 because of the dimension of the system. So there is an amplification of 3 plus the surface of the oval window is smaller than the tympanic membrane. So if I apply pressure to a smaller surface, if I apply a force to a smaller surface, of course the pressure will increase. And this increase is almost 30 times. So 30 by 3, we got 90 times increase of sound pressure level. As I told you before, there are the resonant effects of the acoustic meatus, and in addition there are the brain case that acts as a sounding board. Now, I don't know if you have ever tried to listen to your voice recorded. Your voice, when you speak, sounds in a way. When you listen to your voice, it's a completely different way. Because of this effect, because brain case acts as a sounding board, it's like a guitar. So, 3 by 30 is 90. These two components give an increase of 10, the total increase of sound pressure level because of the ossicle is almost 100 times. And we are on the interface between the inner ear and the outer ear. The sound director window, and basically walk all this way. This is the dicotrema, the little hole which connects the scala vestibuli with the scala tympani. So sound comes here, and depending on frequency, walk all the cochlear duct. Because as you know, if a sound has a frequency, if something has a frequency, it has to have also a wavelength, so a length, a physical length. As you can see, if the frequency is high, means that the wavelength is very short, so the sound will impact the first part of the cochlear duct. If the frequency is very low, means that the wavelength will be bigger, and the sound will impact this area. So, high pitch sound, high frequency sound will affect the starting part of the cochlea. Low frequency sound will affect this part of the cochlea. 16 kHz and 63 Hz, actually 20 Hz to be here, it's 20 Hz, are the auditory range of human ear. When you were young, younger than you are now, you can feel sound in the range 20 Hz, 20 kHz. When you get older, it's sad to say, but you lose the high frequency. So your system will be able to detect frequency from 63 Hz to 16 kHz. So we lose the range from 16 to 20 Hz. It's totally natural. There is no way to avoid this situation. So, feedback on this drawing. The vibrations are propagated through this scala vestibuli and through the dicotrema, which is this little hole, go and walk through the scala tympanic. At the end here, there is a round window, or the round window, which allows the perilymph to move, and when perilymph moves, basically it makes the tectorial membrane of the organ of Corti moving too. So we can connect the tectorial membrane to the organ of Corti and create an electrical stimuli that can be detected by our brain. And this is more or less the description of our organ of ear works. Now, we have a body and we have a sound. And every person is different, because my ear will be different from another one. And the problem is that when we work as an engineer, we can say, okay, Alessandro feels this sound in this way, Giuseppe feels this sound in this other way. We need something standardized. And here comes the psychoacoustic, which is a study of how the sound is detected by the average jaw, so an average ear. This first picture is the audibility diagram, also called in Italian diction. Well, I don't remember that, I'm sorry. How it's made. On the x-axis there are the frequencies from 20 Hz to 20 kHz. While on the y-axis there are the sound pressure level. This diagram was created by two guys in the early 90s, Fletcher and Manson, which were two physicians, two physiologists, two doctors, two geniuses. They tried to simply, they took a big number of people and they start saying, okay, I'll give you a 50 Hz sound, and this sound has a pressure of 20 decibel. Could you hear this sound? No. Okay, I'll give you a 50 Hz sound with a sound pressure level of 40 decibel. Can you hear this sound? No. Okay, I keep increasing the sound pressure level. Let's say that it's 45. Can you feel this sound? Yes. And they mark this portion. Then go with 100 Hz and do the same thing. Can you feel this sound at 20 decibel? No. Keep going with the sound pressure level. Can you feel this pressure that has a level of 38 decibel? Yes, and they mark this point. And they built all these curve. Okay? Which is the threshold of hearing. That means if a sound at different frequency has a level below this threshold, we cannot hear that. And in the same way, they do the same stuff with the music and the speech region. Now, I'm just interested in this section, threshold of hearing and threshold of pain, which is the upper limit of this diagram. But in acoustics, when we want to design, for instance, a concert hall, we are interested in this area, in the pink one. Okay? Because we want to know that when the sound starts, we can perfectly feel the sound. The guy who made this auditorium, I guess, tried to optimize the behavior of this wall to stay in this region, in the white one, speech region, because this auditorium was made for making talk, for making speech. After this diagram, which is the dipole diagram, comes this one, which is basically the same diagram. As you can see, there is a threshold of audibility. And this diagram was the real diagram made by the Fletcher and Manson, even if here it's called ISO, International Standard Organization 226/2003, because it was uploaded, upgraded in 2003 with new technologies. The measurement was made one more time in order to be more accurate. What this diagram means, you can see there are, like, again, frequency, sound pressure level. What are these numbers? These are the phone, so-called phone. It's the auditory sensitivity. That means that, let's consider this line, the 10 phone line, a sound that has 100 Hz and a pressure of 30 Hz will give you the same sensation of a sound that has 2000 Hz but a level of 10 decibels. So I can feel different sound with different frequencies. If you want to study the problem that affect the human ear due to sound, we need to talk about these guys. The inverse of the isophonic curve, basically the mathematical inverse of 40 phone curve, 60, 100. We take this value, we make the inverse, the simply mathematical operation, and we got this other diagram, which is the frequency weighted curve. What does it mean? This is a really important diagram. As you can see, there is the A line. So this blue curve will be the A frequency weighted curve. There is the B one. There is the C, which are basically the inverse of the 40 phone equilogous curve, the inverse of the 60 phone equilogous curve, the inverse of 100 phone equilogous curve, and the inverse. Don't consider this one, please. It's not. It's just for airport full noise. We are not interested in this one just today. Now, in your opinion, and this is a question that I always give to my students in Italy, what does this diagram mean? Because I say, okay, Giuseppe, talk me about the Fletcher-Manson diagram and talk me about this other diagram. They start saying, which is the frequency weighted curve? Oh, it's just the inverse of 40 phone. Okay, nice. And so, what can you say? What can you tell me about this diagram? I'm not letting you, so please speak freely. You can say whatever you want here. Any idea is good. Over there? No, I'm not your professor, so you can say more. Your professor is not listening to you now. So? No? Okay. We have just to expect plot. It's easy. We got frequency, we got an increase or a decrease, we got a gain, an attenuation or an increase. And after all, everything is right here. So I've got a sound. As I told you, this sound may have for sure different frequency. So every frequency I have subtract or add a value, because my ear can feel a 100 Hz sound as a 1000 Hz sound. So because my ear has a different sensitivity, a different frequency, I have to correct this behavior using this curve. So take an example. I've got this sound 100 Hz. I want to apply the A frequency weighted curve. So the sound pressure level at 100 Hz, I go here. I have to decrease the number that the instrument gives me by 20 decibels. So if my instrument gives me a sound pressure level of 100 Hz, 100 decibel, at 100 Hz I need to reduce the sound of 20 decibels. I've got a sound of 80 decibels. The same stuff of the example. 200 Hz. We go to this curve. We say, okay, a sound, the same sound at 100 that has a level of 100 decibel. If the frequency is 200 Hz, I need to decrease the real value of 10 decibel, just because my ear feels this sound in different way at different frequency. Okay, is it clear? No? Okay, do another example. I got a sound, okay, and this sound has a sound pressure level of 80 Hz, 80 Hz. But this sound is made of different frequencies. So I will take an easy example. It's made of two frequencies, 100 and 200, okay? I go on this curve and say, my original sound, linear sound, has a pressure of 80 decibel. But because of the frequency of 100 Hz, I cannot feel in the same way. I need to decrease the 80 decibel of this value around 20 Hz. So my sound won't be 80 decibel, it will become 60 decibel. I do the same stuff with the sound at 200 Hz. In this way, I can correct all the frequency of the sound, because a way is there is a manner is the way in which the instrument detects the sound. Another way is how Alessandro, how real person, can feel that sound. So I have to take care of this difference between the instrument, which is like just microchip, just filter, and me, which is a real person. Okay, and we do this using this diagram, which basically becomes from here. Okay. These two guys make all these experiments of a big number of people and come up with this diagram. If we invert certain curves of this diagram, we got this, which are basically a kind of correction factor for each frequency for every sound at every sound pressure level. Okay? Got it now? So we already talked about this stuff yesterday when I introduced the concept of equivalent continuous level. I told you that the sound usually has this trend, so it's really fluctuating. But because it's difficult to say, this sound one time is 57.5, the other time it's 56.5, the other time is again 57.6. It's really difficult. We want to use a mean value, okay? The most important thing about this plot is the area of this part of the graph. The area of the blue line, okay, is equal to the line, to the area of the black line, okay? So the energy produced by the fluctuating phenomenon, which is the blue line, is the same of the energy of the stationary phenomenon, which is the black constant line. And we can do this evaluation applying this formula. I put this slide because yesterday I talked about this descriptor, but I can understand was something really smoky for you, because I talk about the fluctuating signal, the stationary signal, but if you don't see this plot, maybe with this plot now everything is more clear, at least I guess. Is more clear? No, not so much. Okay. Stay on this one more time. When we collect a sound, this sound may change its sound pressure level, so the number on the y-axis. In this way, it's really random, okay? And it's really hard to say, one time my value of the sample pressure level is 57 point something. The other time will be 57.2. The other time will be 57. I can do this. Because when I want to analyze the data, I need a single data that represents me the phenomenon, okay? So, I said, instead of using this changing, okay, up and down sound, I can substitute this, I called fluctuating noise, with a constant noise which has always the same level. So I can say, my sound, instead of having a pressure that sometimes is 57 point something, the other time is 57, the other time is 57.2. No, as always a constant level of 56.5. So the the energy of my sound from 0 to 360 seconds, because I have to refer this lag to a period t, in this example from 0 to 360, it's constant. The sample pressure level is always the same, it's always 56.5. Okay? So I can summarize all this information up and down in 360 seconds with a single number which is 56.5. It's clear now? And I can do this simply putting this equation where P is the pressure of the general value of this fluctuating noise. P con 0 is the reference pressure, which is 20 micropascal. The T is the sampling time, so the interval, in every millisecond I sample my sound. T is the length of my measurement period from 0, so in this case it will be 260 seconds, and 10 times log is just a mathematical operator. So if we plug all this number of the blue line in this equation, we can get this black constant line, okay? Do you believe me now? Oh, of course, now we have to try to figure out if this equivalent continuous frequency weighted level is a good or bad descriptor for noise of water. So I told you that this. Everything clear? I mean, there's like people talking. Huh? Yes, I'm here, so just ask me a question. You can ask me whatever you want. Don't be shy, please. Okay. So I told you that in this way we can summarize all the variable phenomena just with a number. But in this way we lost a lot of information, because we lost information about this point, we lost information about this point, we lost information about this point. And this, for our goal, is not very allowable, it's not very good. Because in this way, LAQ cannot completely describe all the sound characteristics, especially if the phenomenon is extremely dynamic, as in this case, okay? Because I'm losing information about all these other points. I guess we can switch this slide because we already talked about the single event level yesterday when we condensed all the sound pressure level given me by the lab in 1 second. So I guess this is something we can just skip. And here comes the impulsive noise. Question? Okay. This is the definition of impulsive noise. So, noise which is really fast in time, as you can tell from the name. Impulsive is something like happen for fraction of second, for really small time, but as a big value of energy. So how can we define, according Italian and European directive legislation, if a sound is impulsive or not? Just make the difference between the sound sampled with this constant, so with the impulse constant, minus the same sound sampled with the slow constant, which is basically the red line minus the black. If this difference is almost, it is at least 6 decibel, we can start going to the second check. If this point minus this point is bigger than 10 decibel, then 10 decibel, and this time interval is smaller than 1 second, so this component is called impulsive, because soar very fast and reach an high value of pressure and then decrease. This one again soar really fast and decrease really fast. And if these components happen 10 times during the day reference time or 2 times during the night reference time, we have to say that this could be a problem for the human health, okay? Because our body can support too many impulsive noise events. And why they are harmful? Okay, now I need one of you here. Come on. Anyone? Iga, come here. As I told you, we have to match a body reaction. Great. It's this one. We need to collect a stimuli. No, not because our body is made of muscle, is made of nerves. This muscle has a reaction time. These guys are really fast. We are talking about milliseconds. A reaction times is a fraction of a second. So, I told you about the stabilis muscle. Because it's a muscle, it takes time for the brain to recognize the problem. Say, okay, stabilis muscle, contract the ossicle so you will move less, and then coming back this information. It takes time. In this time, this sound has passed through the tympanic membrane, okay? So, the protection of the stabilis muscle, because this guy is very fast, is not effective. And for this reason, impulsive noise, even if they are not really high in level, are really dangerous because our body can protect the tympanic membrane from this kind of sound. Basically, the sound passes through, and if the sound is very high in pressure, may even damage the tympanic membrane. Literally can make a hole to the tympanic membrane. And if your tympanic membrane gets damaged, you lose your organ. Okay? Tell me.
For example,
okay, it's really common. I'll show several examples down the way. But shotgun, when you shot with a gun, it's an impulsive noise. It's really high pitch and it's really fast. For this reason, when you go to the polygon to shot in the right place, you have to wear a muffle because you have to protect from this kind of events. So, stabilis muscle reduces the ossicle excursion with the time of a muscle reflex. If this is, let's say, a fraction of a second, but this is in the order of milliseconds, this sound simply passes through the tympanic membrane and there is no protection from the stabilis muscle. So the mechanism we got in our head for protecting our body from this kind of phenomenon is basically useless. Okay, here comes the legislative scenario. I got a little comparison between the system we used to adopt in Europe. This is the directive 2003-10 European Community. This is the name. European Parliament of the Council of February 6, 2003 on the minimum health and safety requirements regarding exposure of workers to the risk arising from physical agent to noise. This is just the name. In Europe, tell me.
This reaction in our body causes every effect with our health, especially in our heart. No, the effect in health is not only our ear and cerebral activity, affects all.
You mean like when you are really chilled out, a big noise happens?
I think that the principal effects have in our heart
Yeah, okay, I got what you. No, I guess the main problem is for our ear, because besides if you're not a really old person and if you don't have any heart disease, really, like heart stroke, it's really difficult for like an impulsive sound to damage your heart. I mean, you can be like shocked for a while, but you won't die. I guess, I hope, if you're not like a really pathological situation. But if an impulsive sound passes through your air, you lost your timpani. And once your timpani is lost, there is no way to come back. Okay? No, you won't. So, back on the legislative scenario. We got these two directives. In Europe we use this one, while in the United States we use this other one. Since my university is in Italy, we are more focused on this directive. Just a little spoiler, we are working on a new paper and try to match this directive with this other directive and try to find which of the two is the best one, which are the weaknesses and which are the pros of these two directives. So, our lovely directive use these parameters for evaluate the noise and the protection of workers. It's the daily noise exposure level, called LX 8 hour, because it's standardized, it's normalized to a working day of 8 hours, so they absorb those by the workers or by the worker in an 8-hour day. The weekly noise exposure level, which is basically the same stuff, instead of being standardized on 8 hours, it is standardized on 40 hours. So a week made of 5 working days, each of one has 8 hours of working. And they both are the time weight average of noise exposure level for a nominal 8-hour working day. This means it's the LAQ, the LAQ, evaluated on 8 hours. The funny thing is that these two parameters covers all the noise present in the workplace. So there is no distinction if there is an impulsive noise, if there is a tonal component, it's just noise. They don't say, okay, this is like 80 decibel, but maybe it's an impulsive noise, so it's more dangerous. No, it's just the level of the noise. Because the protection from impulsive events in their idea, in the idea of the directive 2003-10 AC, is provided by this parameter. The C frequency, weight, peak sound pressure, which represent the maximum value of the instantaneous C frequency weight. So the sound with the C curve I showed you before applied on. Do you remember the frequency curve before? If I get this sound and I apply the penalization, I got this peak maximum level of the sound pressure level. And as you can see, it's like a full parameterization of a complex phenomenon, because just three parameters want to describe a complex phenomenon. And these are the maximum admissible level suggested by the directive. So the sound is not harmful if the LX 8 hour is below 80 decibel. The peak pressure sound, if this value is below 140 decibel C frequency weight, the sound is no more admissible, because this value is the maximum admissible value. If the sound pressure level is equal to 137, the worker has to be supplied with individual hearing protection, so ear muffle, headset, and whatever. While if the pressure is below this value, there is no need for the worker to wear protective equipment. So if I got a sound pressure level at a peak value below this threshold, I can stay in the sound, and according to the directive, is not harmful for me. What time is it? Because I guess we start later.
3:20. 3:20.
Okay, so we got time. 40 minutes. We can do that. the study we are doing with my university in Italy in the last 15 years. Alfredo and Occo started this brand 15 years ago. I just started 5 years ago after my graduation, is to try to align all the weakness of this directive. And we point out, I guess, 3 main points. The first one is this. If we use just the lack on the week and the lack of the day and the lack of the week, this value cannot identify in a proper way the noise and the effect on the health of the workers. This because impulsive events, I told you, they are very short in time, but they are very energetic. If I try to consider these impulsive events in a day, which has a length of 8 hours, even if I've got 170 decibel, a big sound pressure level, but just 1 second, if I go to make an evaluation on 8 hours, you can imagine that 1 second, 1 simple second, cannot affect the level on the 8 hours, isn't it? Because if I make a kind of average, 1 second on 8 hours, it's, from an engineering point of view, from a medical point of view, it's nothing. So, impulsive events contribute in the determination of this value, but they are not considered as single events. They concur in the evaluation of these parameters, of these 2 parameters, and they are not separately considered as dangerous effect to the human ear. Is everything clear? The poor girl with the yellow shirt. No. Guys? Yellow sweatshirt? Is everything clear? Hey? Okay, better. Then comes the weakness of this parameter, because this parameter cannot evaluate the incident energy on the human ear. For 2 simple reasons. Here we fix this value, okay, 135. If you remember the first slide I showed you about the Fletcher and Manson diagram, do you remember there was like a threshold of hearing and threshold of pain? The threshold of pain value, do you remember what it was? More or less? A number? Come on. Was 120. So after 120 decibel, I start feeling pain. Look here. According to directive, there are 50 more decibels I can simply keep without feeling pain, without wearing protection. And another thing is this. I have to apply the C frequency weighting curve. So my level, my original level, is even higher because when I apply the C curve, I artificially decrease the value of the pressure. So I'll show you several examples. A sound that maybe could have a pressure of 150 decibel linear, when I apply the C frequency weight curve, could decrease up to 120 decibel. So we are below this limit, no air muffle, no protection, but my sound is 150 decibel. So it's something really further the threshold of pain. A sound of 150 decibel can easily break your tympanic membrane. It's like stay on in an airport when an airplane is taking off. Just to give you an idea of the noise of 150 decibel, okay? In these 15 years with my university, they had a lot of fun sampling, working noise produced by office activities, noise produced by public transportation that affect public transportation drivers, noise produced by university and research centers and laboratory as mechanical lab, engine testing room, materials stress testing lab, etc. And industrial activities of the industrial sector. This was because several judges, several courts want to know the effect that the sound pressure level may have on worker. So they just go to my university and ask them to make surveys and to check if the noise environment was safe or not to the worker. And they achieved this procedure using this little guy. This is actually we have this in our lab. We use this one because it's cheaper. This is called dosimeter. Okay, is a device placed on a on the shoulder of the worker. Why is placed on a shoulder? Because I want to know the sound that affects my ear, so I have to stay close to my ear. I put this stuff, which is a microphone, an analyzer, and this guy allow like a data logging. So for 8 hours I can sample the sound pressure levels that affect the ear, okay? And in particular we use this model for Gladstone and Davis. This device to a person, and we told them, okay, you have to wear this stuff for 8 hours and just do your work. And we got this result. This is a sound pressure level for a 5.5 working day, 5.5 working day, in a factory of cast iron production. As you can see, the blue line is the equivalent level, and the peak value is are the red lines. So we got this signal. Applying the formula I showed you before, the LEC formula, we can get this data, 73.1 decibel, a frequency wave, okay? But this datum is about 5.5 hours. The standard told me that I have to evaluate this data on 8 hours. So I simply scale this number on 8 hours, and I get a smaller number, 71.5. You remember the limit of the standard was 80 decibel. So according to Biotech, this parameter is not, it's safe, because 71 decibel in 8 hours, like according to the standard, is safe. The peak value, we go there, check the maximum, is over there. It's 118.6 decibel, which is always below the 135 decibel. So, if I apply the standard, all the values, LEC and peak, are below the directive limit, and there is no obligation to wear the personal protective equipment. Another example, always the same working activity, cast iron production. We do the same analysis. We go to this guy and told him, okay, wear this stuff for all your working day. We analyze data. We got a LEC on 5.5 hours of 74 decibel, which scaled on 8 hours becomes 71.5. And a peak unweighted of 141.5 decibel, which is really high. But when I apply the C frequency weight curve, look, it decreased. And remember the limit is 135. So even in this case, there is no way that the worker can wear the PPE, because both limits on the LEC and on the peak are below the threshold of the directive. And this, to conclude this part, is an evaluation of the noise which office workers are subject to. Simply is secretary work. We got a LEC of 61 on 6 hours, which scaled on 8 hours becomes 51 decibel. A peak sound pressure level of 130.7 dB, which when the C frequency weight curve is applied becomes 118 decibel. In this case, there is no reason for the worker to wear protective equipment. So, to sum up, according to the directive, everything is fine, because this value, everyone are below the threshold limit. But what about the threshold of pain? This one, 140, look, is here. It's far below the threshold of pain. So it could be a serious problem for the worker. But according to it, because this number, when the C frequency weight curve is applied, is below 135, everything is fine. So this is the first weakness of this directive. Of course, the peak value depends on the frequency, on the content in frequency of the content of frequency. Take this example. This is a sound pressure level sample for a worker driving a bus, a diesel bus, okay? As you can see, when I apply the correction, there is no big difference between the linear value and the C frequency weight value. But if I consider this methane-fueled bus, as you can see, I've got a peak linear of nearly 150. When I apply the C frequency curve, it becomes 133, so below the limit. As you can see, this normative doesn't consider about this effect, okay? So, again, if I apply the suggestion of the directive, my water is safe. But as you can see, I've got a peak pressure level, several times. I've got 1, 2, 3, 4, 5 really big pressure level peak that can, of course, in long time, damage the system. Is everything clear? Okay. So, what we suggest? Since our ear, okay, may feel in different way the sound wave, but the pressure that affects the system is always this, keep continuing using the linear as the previous directive used to do. This was the previous directive before the 2003 was applied. If this limit were still considered, the bus driver was forced to wear protective personal equipment. So we suggest simply to step back and come back to the previous directive, which is more safe from a worker's point of view, because there is no need to consider an exposure value and apply a C frequency weight curve, because the pressure that is effectively impact our auditory system is 149 decibels. It's not this one. This is how we feel, but the pressure is this. Okay? You got this step? You got this passage? Yes? No? Maybe? And this is another point we'd like to highlight about the weakness of the directive. This is a 30 minutes measurement made in a mechanical workshop, I guess. Yeah, it should be a mechanical workshop. As you can see, there are several peaks, okay? The length of this plot should be around, let's see, 95 decibels, okay? But it's just a 30 minutes time. When I scale this number, this 95 decibels on 8 hours, I will be for sure below the 80 decibel, which is the limit of the directive. But look, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 peaks that are above 120 decibel. So they are above the threshold of pain. The directive doesn't consider them. They just say, okay, make an evaluation of the lag. If this value is below 80 decibel, everything is fine. No need to, there is no consideration of this event higher than 120 decibel. So this is another weakness of the directive. Okay. So if the sound is stationary, that means it's constant, our ear can adopt a kind of defensive mechanism, because it's like if it's saying I've got a sound which is always 90 decibel, I know how to protect. But if the sound changes its value in time, it's really fluctuating, our ear, because it's made of muscle, because it's made of nerve, can keep up with the real phenomenon. And so this directive is not effective against sound characterized by a persistence of 2 milliseconds as impulsive noise, which are just impulsive, just so they eat and run away. They pass through the membrane within the protection of the stabilized muscle, again deactivated. To conclude, we made several progresses. The community made several progress in the protection of water, because several laws were made and new applications were provided. The European directive can individuate the most common critical situation, but sometimes it fails because we not guarantee the protection of the worker, and in particular of the most sensitive part of the human ear, such as the tympanic membrane, when an impulsive noise happens. The acoustic characteristic of the workplace cannot be just represented by these three values. We need to implement this value and using even more descriptors. And in addition, the C frequency weight curve that artificially decreases the signal energy at low and high very frequency and at low and very high frequency parts is not a suitable way, because again I'm going to consider a sound that in reality doesn't happen. In a mathematical operation I'm doing on this signal. So what we suggest: evaluate separately the contribution of the impulsive component. So don't consider the impulsive component in these two parameters, but say, okay, my level is 78 decibel, so I'm below the limit, but I've got 10, 11, 20 impulsive components that may damage my human ear. And don't use anymore the C frequency weight, because again it decreases in artificial way the real pressure of the sound.
Muchísimas gracias, ingeniero. ¿Alguna inquietud referente a la temática?
Sí, pero tiene por el fenómeno.
Por favor.
Entonces ahí había una parte donde tenemos, entonces si puede salirse de ese rango, siempre tiene que salir de ese rango en esa área de auxilio.
If you want to listen to music in a place, you should stay in this area. Of course you can go outside, but if you exceed and you go too far, you go in the threshold of pain area. If you stay too far, too low, you can feel the music. So this is just an optimum range, okay? It's the optimal situation. In a bad region, because you're applying you're applying to this guy a sound in this direction. So try to, I know, I don't use them, but try to use the muffle, not the itself.
What is the difference in the closed area from the wall to the SPL in the worker? Maybe it could be less range that
A wall is a bad effect, because if I reduce the area, I simply can saturate the area in an easier way. And if I, as I told you yesterday, if I stay close to a wall, I've got the direct effect and the reflection, so I can increase the effective sound pressure level that I'm applying on my system.
but in the range that you have to use EPA, it increase. In the range that you have to, the workers have to use EPA, it increase.
No, it's reduced.
Yeah.
I mean, you should reduce the limit.
Yeah, but the walls
Increase the effect of the pressure, yeah. Because you got it's not a free field condition, becomes a it's called in English reverberant field. So you basically are increasing the sound pressure level, because again you get the direct wave, you get the secondary reflection, third, fourth, sixth reflection. And as a general effect, you are increasing the pressure, the sound pressure level of the area. But you can put a wall to divide the working area by the worker, so in this way it's like a physical barrier, and you prevent sound from passing from the working station to the I don't know, rest area or to the worker place. But of course you can always put a wall. If I'm welding, if I'm grinding a material, I have to stay there and look at the material. I can say, okay, I put my machine here and I go in another room because I need to use the equipment. Okay?
Because, for example, in an industry that all the machines are in the same area, but only one produces a lot of sound. I would like to know how to avoid the sound to the other people.
Putting a wall. Yeah, it depends on the machine, of course. Usually you can put a wall and separate, like creating like a tomb and putting the machine in this kind of tomb so there is no sound propagation to the other machine.